So now let's look at entropy change calculations, and we'll begin with solids and liquids. So we begin with the equation that we had, that we have ds is du over t plus p over t dv. But dv is really very small for solids and liquids. It's really hard to make a big enough change to make the change in volume measurable. And so therefore, du over t really is the dominant term, so we can say that delta S is very approximately equal to du over t. Now, we also know that frequently we can say that Cv dt is a good way of estimating du. If I have data, I should use it, of course. But if I don't, then Cv dt is a good way to estimate du. And so therefore, if this is constant, which it frequently is, then I can say that it's Cv times the natural log of T2 over T1. Now C sub V and C sub P being essentially equal to each other for solids and liquids, I end up with usually this is the way I write it. In our textbook, they just suppress the subscript, so it's just C ln of T2 over T1. But if you were to look this up in any normal textbook, like a chemistry book or something like that, you'd be looking up the heat capacity, and that would be C sub P. Now, one thing that's important to note here is you have to use Kelvin or Rankine. This was a thermodynamic equation, so we must use thermodynamic temperature, which means Kelvin or Rankine, those absolute temperature scales. When we calculate, say, delta U or delta H, because du is Cv dt, we could have said Cv or Cp times delta T. And when I do temperature differences, it doesn't matter. But now, because I've got a temperature ratio, I must be careful with my units. So if we do an example, let's just look at liquid water being heated from 20 to 50 degrees. And I, of course, could go through and look this up in property tables because compressed liquid water data is available. But let's do it using this equation. So C sub P is roughly 4.2 kilojoules per kilogram Kelvin. 4.18 maybe would be a better value. Sometimes you'll see 4.184, but 4.2 is rough, so it'll work well enough. And then I want to convert my temperatures over to kelvins. 50 plus 273 was the final temperature, 20 plus 273 the initial temperature. Take that ratio, then take the logarithm, then multiply by 4.2, and we get a change in specific entropy of 0.409 kilojoules per kilogram Kelvin. Pay attention to the units. These are not energy units. Entropy units is energy over kelvins. So we're going to take a pause there, and we'll come back and look at ideal gases.